Hello, legends. This is Mr. Maze. Super excited to be reaching you from the digital space. And today we're going to be doing 8.3 video notes, which of course, as you know, and as you could probably guess, will be doing confidence intervals. Of course, you should probably remember my V in confidence intervals. Confidence intervals for two samples. But this time for means, okay? And of course, that's a clunky way to write it. I should say a two-sample confidence interval for means, but however you want to go about it, you can write that out. You'll notice this set of notes starts on slide 20 on the slideshow presentation for 8.3. Before that, and I highly recommend this, you should go through all of the answer choices and responses for the 8.2 homework, along, of course, with the different multiple choice questions that were missed heavily on the Unit 7 test, and the FRQ responses that did the best for that same Unit 7 test. Okay, so it's a beautiful thing. Make sure you're clear on all of that, because as we've started to notice this unit, and as a lot of people have said this unit, it's not that this is bringing too many new ideas to the table, right? The adjustments for two samples are slight. The big things are just making sure that you have everything down hammered, pat, certain, and that you understand the slight shifts that we go through to fully prepare ourselves. So with that in mind, let's roll ever forward, okay? In slides 21 and 22, I go through this whole sampling distribution idea that you should already understand. And of course, we're dealing with sample means. And the way we set them up is we do sample mean 1 minus sample mean 2. Okay? And that's effectively what we're doing, is we're creating an entire sampling distribution where the mean, or the center, is presumed to sit as ostensibly no difference, right? So in this case, the idea would be that the difference in means is equal to, that should be for 2, not for 0. But I was trying to get ahead of myself. For 2 equals 0, right? We assume the center of this distribution is a value of 0, and then there are various amounts of striation that go in either direction, suggesting more and less likely outcomes that are close or far away from that value. And that image is on slide 22 for more detail. Slide 23 is where we really start rocking. The first P in panic, because of course we are doing confidence intervals. And anytime we are doing confidence intervals, we are doing panic. Now I have good news for you. As you might remember, with confidence intervals, we never pool values. We never have to pool a value in confidence intervals. So all we're gonna do for a two-sample T confidence interval for difference in mean is we're gonna start by just defining what we have to do. We have parameter 1 and we have parameter 2. And those will always begin the true mean something. The true mean something. The true mean height for high school students. The true mean hair length for, I don't know, male models in the 80s. Let's just make up some bizarre topics, right? And you will state those at the start of your problems. And that's the first start. That's panic. Our A is, of course, the assumptions. You've done this many, many times before, but of course, now we're doing means again, so cast your mind back. Let's look at those assumptions. Well, for means, just like with the proportions one, we do need to check for randomness. That should be stated in the problem, that it is a random sample. We also need to be sure it's independent. Now, there are two ways it will present as independent when it comes to these hypothesis testing, or I should say confidence interval problems, right? Option 1 is we do 10 times n and we presume that's less than the total population. Now the other option, as is stated on slide 24, is if it is random assignment. And by that I mean if we have a control group and a treatment group of some kind, and we are randomly assigning our volunteers to one group or to another group. The second we do that, you actually don't have to check random or total population being greater than 10 times our sample size, because random assignment takes care of independence for us. So be aware those are your two options. I'll even highlight. It's either this, right? Or it's these two. Those are your kind of go-tos when it comes to specifically these types of problems, right? Because with two sample situations, we often have experiments on our hands. And if we have experiments on our hands, we really aren't going to be able to just ensure that it's absolutely random in who's coming, right? And therefore 10 times our sample being less than the total population is much less important than the fact that we've randomly assigned to the two groups. Other than that, we lastly need to check for normality. Now remember, we are not doing the large counts conditions because we're doing means, so we will do the central limit theorem, and what that states is n1 must be greater than or equal to 30, and n2 must be greater than or equal to 30. Remember, the other option is if the sample data is approximately normal, that's another option. And of course, what that means is no huge skew and no outliers. So that's another option, right? And then, of course, the other side of it is if it says the population is approximately normally distributed. So the same stuff as we've always had when it comes to normality. This is the best thing about this unit is it pulls on all the sampling distribution stuff and all the stuff we did in Unit 6 and Unit 7, right? So we know our normality checks and we should be good to go. All right, heroes, we've checked our assumptions. We now know that we can do these various magical processes, right? So now we're going to name what we're going to do, and ostensibly what we are able to do is a two-sample, because now we're not doing one sample, we're doing a two-sample t-interval for what? For mean 1 minus mean 2. Remember, we are estimating the true population mean difference between these two means, right? And because we've differentiated those two means up for parameter, it's easy to write it this way. So a two-sample t-interval for the two means. Why is it a t-interval? We're likely going to get the standard deviation for the population. On slide 26, we see the format that we should expect. Remember, we are not necessarily, and this is for the I, we are not necessarily going to calculate this by hand. I would recommend not calculating them by hand, unless you're an absolute wizard of hand calculation, right? And the reason why is it can get pretty ugly out here. But here is what it will look like. You'll see it's on slide 26. The reason I want to show you this, other than the fact that I love making sure you guys understand what the work is that your work stands on, is that you may get a multiple choice question where things are formatted this way, so you need to be sure that you understand. Remember that this green part represents the standard error, right, or the standard deviation of the sampling distribution. And then your sample statistic is here. And in this case, it's the sample statistic of difference between the two. How do you do it in real form? Well, you're going to run it on your calculator. You're going to do stat, test, two sample, t int. Okay, get that right. It's two sample t int, and we are not going to pool. We are not pooling. We don't pool for confidence intervals. We, in fact, only pool for hypothesis tests, and in this class, we really only pool for hypothesis tests for proportions. We do not do it for means, okay? All right, this calculation should make absolute sense to you. On slide 27, I go into more detail on pooling. I would read through those explanations, but I believe I've explained this already. We really don't pool. There's a rule called Welch's rule, and we use Welch's rule. We do Welch type calculations. Yes, like the fruit snacks or like the grape juice. We do Welch type calculations when we are deciding, hey, let's not pool. And in the case of means, in this case, we don't pool because we can't trust that the variance will be the same between the two samples. Okay? And to go into detail one more time, if we go to slide 28, you will notice we have to put all the values in for two-samp t int. Okay? Do not mix up what the outputs will be for two-samp z int, or t int, I should say. Know what they are and know what they're doing. And then finally, if you are given raw data, I want to make this clear. Here's what you will do. You will go onto your calculator. Okay? It should be in front of you. I'm pulling my calculator out now as we speak, heroes. And what you will do is you will click stat. So this is in the situation where you only have the raw data, right? You only have the two samples raw data. You'll click stat. Don't go over to test. You'll click edit, which is the first option under edit, okay? That will take you to L1 and L2. Just put the data in and click enter after each data. Click enter after each data point. Do that for L1 and for L2. So this is for sample 1, and this is for sample 2. And remember, this is in the case where you just have the raw data. You don't have the sample means. Okay, you'll input those. Then you will go and you will do the same thing. You will then do stat, test, toSamp, tint. And then you will do specifically, right? Instead of doing stats, you will do the data option, right? There's an option there that we normally click the stats part for. You'll click data, and that will highlight L1 and L2 automatically. And then you just do enter and everything works. When you want to clear the data, what you do is pretty simple. Go up to L1 or L2, whichever one you want to clear. So go highlight above the data itself, go to the very top when you're in stat edit, go to the very top where it's highlighted over L1, click enter. Then once you've clicked enter, click clear, then click enter again. And what you will see is that all of L1 then clears itself and you can fill it in with new values. So just as a side note, that is how you calculate raw data using this particular function. One of your homework problems requires that, so I want you to be clear on it, okay? Be aware, obviously, if we're doing it by hand, we might use degrees of freedom, but if we're using the calculator, use the calculator functions and input what they ask for, which are the sample sizes. So you're gonna kill it. Alrighty, my heroes, my legends. What we do is we then conclude, and you know this like the back of your hand. What will that look like? We are blank % confident. Again, don't give me confidence level, give me confidence interval here. That the true, and in this case it will be difference. Oh, my handwriting is hideous. It's because I'm doing this right after teaching you wonderful legends. So I have given all my energy. I left it all out in the field, folks, I promise you. I left it on the court. The true difference in mean, and then you'll explain context on that. Mean high school students' heights. And obviously it'll be the two ones. So it'll be in mean high school students' heights that are male and high school students' heights that are not male, is between blank and blank. And that's what you'll do. That is the entirety of what you will do. You will also notice on slide 31, I give a perfect definition of confidence level in context when it comes to, in particular, mean difference, right? Two sample mean differences. So I'll just say this one out loud, but you should read it on slide 31. If we took many random samples of the same size and constructed a blank confidence interval to estimate blah, 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 like mean difference between these two values, to around 95% of our confidence intervals would contain the true population parameter, and you would give context for that. Now, the last slide of big importance, or last set of slides of big importance, are 32 and 33. And just remember that paired data is matched data. It's data where the values for one set and the values for the other can be mathematically worked with together, so where you can subtract each value from each other value because they're paired together, either because it's the same one-to-one situation or because it's matched up. And we will go into more detail on this in the 8.4 notes, but just be aware that you have to have a counterpoint for each value if you want to use paired data. Paired data means, like we learned last unit, you can just do a one sample t interval for paired data. And you will have mean difference and x-bar difference, as opposed to having two data sets, which is what we're doing here. And with that, we don't have a matched pair, right? Every single person does not have a corollary in group 1 versus group 2. We can't just match people up as identical. It's only when we have like twins or when we're rolling through and doing examples like the UCLA one, where it's like UCLA bookstore prices and then Amazon bookstore prices, where each book has a corollary in the other corner, or a counterpart, I should say, in the other corner. And that's it, legends. That's all I need you to know. Practice through this. Again, you will notice this is a lot of review of stuff we've already done. There's some slight changes, but it's the same panic with the same interpretive dance I always do. I might even have Miles do it again for 2 samples, just so you keep it together. Slide 33 goes in, as well as slide 34, to kind of further clarify the difference between paired data versus 2-sample data. I am so proud of you. Thank you for being my students. This has been the 8.3 video notes, and this is Mr. Mays signing off.